This UAS tutorial video is brought to you by AmericaView, a nationwide consortium for remote sensing education, research, and geospatial applications. This project was supported by a United States Geological Survey grant, and its contents are solely the responsibility of the authors and do not necessarily represent the official views of the USGS. Mention of trade names or commercial products does not constitute their endorsement by the U.S. government. Hello everyone, welcome to part 4 of our 5-part video series on using small unmanned aircraft systems to assess rainwater harvesting potential for urban multifamily housing. This part of our video series is titled Image Processing, and in it we will discuss some of the necessary steps to take when processing your UAS-derived imagery into 2D and 3D maps. Now that we have acquired our high-quality input images from our UAS, we can now focus on converting those images into a usable orthomosaic map for our rainwater harvesting assessment. For this video, I will discuss 3 main topics. The first topic I will go over is the guiding concepts behind this process of combining images. The second topic I will go over is the list of steps you need to follow in order to process your imagery. And lastly, I will discuss some of the main outputs available with these methods. When thinking about using photogrammetry to derive 2D and 3D maps, we need to first understand the importance of image overlap. Just like I mentioned in the previous video, image overlap is extremely important because it can dramatically improve or diminish the quality of your maps. Overlap is so necessary because the photogrammetry software used will require multiple images from different viewing angles in order to determine distances. This is made possible because the images we are using are geotagged and therefore have locational attributes. Using the concept of parallax, or determining distances from multiple vantage points, photogrammetry software will handle most of the difficult task of combining the images and orthorectifying them. Orthorectification is a significant step in the processing that will help correct for any image distortions due to the UAS's camera. The last concept I will focus on is the orthomosaic. The orthomosaic is our primary map product of interest since we want accurate geometric measurements. It is also worth noting that the 2D orthomosaic is actually created from the 3D data that is generated in the process in order to correct for the distortions associated with features that have higher elevations like buildings. For our image processing, we will be using Pix4D Mapper. I do want to mention though that there are many other software programs available that can accomplish similar tasks. Each of these competing software programs have their own strengths and weaknesses. However, this video will focus solely on Pix4D Mapper and how it is used to accomplish the mapping tasks. So to get started, we first need to open Pix4D Mapper. Once it is open, you will see the options to create a new project or open an existing one. We want to select New Project. Then you should see a new project box open that asks for a name and file location. So we want to name our project. In our case, it will be a garden apartment site. And then we will want to choose our file location, somewhere that is convenient to access. And lastly, we will click Next. Now we need to add our images from our flights. So click Add Images. Then you'll want to navigate to where you saved your images from your flight. And select all of your images. I normally find it easiest to just press Ctrl A and it will automatically select every image in your folder. Once all the images are highlighted, then click Open. Now you want to briefly verify that all images you took are actually selected. In our case, we know that we took 754 images with the UAS, and here it is showing 754 images selected, so we know that all of ours have been selected. If, however, not all of your images are selected, then add more if needed. Then click Next. An image properties box should then pop up, displaying various stats related to the images, like altitude. Use this as an opportunity to briefly scan for any incorrect images that might have been uploaded accidentally. This can usually be caught by noticing if any of the images' altitudes or other stats are significantly different than the rest. Once you have verified that they are all correct, then click Next. Now it will ask you for your desired output coordinate system. This is where you can either select a metric system or imperial system. For our project, we will go with meters as the unit and the auto-detected coordinate system, WGS84/UTM Zone 16 North. Once selected, then click Next. The last dialog box that will appear is one asking which processing template you would like to use. These templates are essentially default settings for certain desired products. In our case, since we are interested in an orthomosaic map output, then we will go with 3D maps. We will have the ability to further tune the settings, so don't worry about the templates too much. Once you have selected your template, then click Finish, but make sure you do not have the Start Processing box checkmarked. We do not want it to start yet. After the Templates box closes, you are then back to the normal map view. In the bottom left corner of the software, you should see Processing Options. Click it to open up more options. When the Processing Options box opens, you'll notice that the processes are split into 3 groups. The first is Initial Processing, the second is Point Cloud and Mesh, and the third is DSM, Orthomosaic, and Index. For this video, we won't go into detail over the specific options since there are many available and they all greatly depend on your specific project. Initial Processing has 3 tabs that are labeled General, Matching, and Calibration. These 3 tabs have important settings that relate to the initial tie-point cloud generation, which is the foundational data used to create the 2D and 3D products in the next 2 processing steps. It is worth playing around with these settings and trying out different options, since the initial processing phase can arguably be the most important for an accurate point cloud. The next phase of processing is called Point Cloud and Mesh. During this phase, the 3D point cloud and 3D textured mesh are generated. The point cloud is an extremely useful product generated in this phase because it is used as the basis for the 2D outputs like the orthomosaic. Under this phase's settings, there are 3 tabs. These tabs are labeled Point Cloud, 3D Textured Mesh, and Advanced. These options for these settings can significantly improve the resolution of your final 3D models, as well as the density of your point cloud and its accuracy. So make sure to try a few different iterations of this phase, but with various settings to compare. The third and last phase of processing is called DSM, Orthomosaic, and Index. During this phase, the digital surface model and orthomosaic are created, as well as a few other products that are optional. There are 3 main tabs under this option that are labeled DSM and Orthomosaic, Additional Outputs, and Index Calculator. With the settings in these tabs, you are able to decide the output resolution or ground sampling distance, as well as which other products you want. Some additional options are contour lines, digital terrain models, vegetation index maps, and gridded DSMs. Now before we press OK, we need to check the Resources and Notifications option too. This option is rather simple and offers a couple settings related to how much of your computer's processing power you want dedicated to Pix4D while processing. This is useful if you wish to still use your computer for other tasks while Pix4D is processing in the background. You can also opt for an email notification when your project has finished processing, which can be quite nifty if you're working with projects that require long times. And now that we are done with choosing our settings, click OK. When the dialog box closes, you'll be brought back to Map View. Before clicking Start, make sure you decide if you want to run all 3 phases back to back, or if you'd rather do them one at a time. Some people find it beneficial to check the results after each phase so you can edit in between steps. Once you have decided, then we can finally click Start. And now it is processing. Just make sure to let it process in peace. By this I mean do not click around needlessly or else you might risk causing it to crash depending on your hardware. As long as the little yellow arrows in a circle are spinning, then your project is still processing. It is easy to get nervous about it being frozen after several hours of processing, but as long as that circle is spinning, then your project is still going strong. After letting your project process fully, then you should be able to view your outputs. When you click on the Ray Cloud tab, this should be what you first see. The layers listed are the various products created during the processing. The first thing you'll see at the top is the cameras layer. This layer displays the location of every picture used to create the outputs. If you click the box next to tie points, then it should display your tie point cloud. This is essentially a simple point cloud that is used to tie all of the images together. This cloud of points is used to create the products in steps 2 and 3. From the tie point cloud, a densified point cloud is created. And like I previously said, this is arguably the most important data created since it is used for the creation of the other outputs that follow. Also, a benefit to newer iterations of Pix4D and related software is that the point clouds can be automatically classified into various land cover categories. This is a nifty feature, however the results are far from perfect and require a lot of manual correction. If you do decide to correct some of the errors, then there is a promising way to do so. As you can see, there are a lot of empty spaces with no points occupying them, and due to this we often end up with incorrectly placed points. By clicking the Point Cloud Editor tool, we can manually correct some of these incorrect points. In this image you can see a selection of highlighted points in red that are obviously incorrectly positioned and are creating error along the roof's edge. By clicking the points and deleting them, we can further improve the quality of the other outputs that depend on the point cloud's accuracy. Since rooftops are our primary concern, then we want less incorrect points so we can achieve straighter edges. Another important output that is extremely useful for 3D purposes is the 3D textured mesh, also known as the triangle mesh. This layer contains an interpolated point cloud that has been smoothed to provide a nice aesthetic and look more complete. Wherever there are empty spaces with no points in the point cloud, this layer has filled in with estimated values. Now if you click over on the Mosaic Editor tab, then it will bring up the interface for displaying the digital surface model, as well as the orthomosaic. For our garden apartment site, our orthomosaic was able to have a resolution of 1.5 centimeters per pixel, which is quite impressive. As you can see when you zoom in, surprisingly, many of the buildings have clean, crisp edges, and there are very little noticeable inaccuracies. If you do notice any warped edges or other inaccuracies, then you can always go back and further edit the point cloud and rerun the steps. But now it looks like we have our orthomosaic ready, and it's time to move on to the next part of the series. Our next part of this video series will be Part 5, Land Cover Characteristics and RH Potential. In order to get a well-rounded understanding of the impacts of rainwater harvesting on a specific site, we need to determine its actual land cover composition. If a particular area has a higher amount of impervious surfaces compared to pervious, then it might be more suitable for rainwater harvesting applications. Understanding these compositions can provide extremely useful contextual information about your site of interest. The topics that will be discussed in Part 5 include land cover classification concepts, creating classes, calculating ratios and areas, and finally calculating rainwater harvesting potential. Thank you for watching.